Good afternoon, everyone. My name is Faraz Banavi, and today I will be presenting my term paper for the Artificial Neural Network course. My project title is Artificial Neural Network based on the stroke risk prediction using health data. So, for our agenda, I'm thinking of proceeding as first of all the abstract part and the introduction, then the dataset and description, methodology, ANN architecture, experimental results, and future studies and the code. As an abstract, developing an ANN to predict the stroke risk using structural healthcare data. I used the Kaggle dataset, and this study was addressed as a nonlinear relationship, and it focused on the demographic and clinical factors. As an introduction, predicting the stroke risk through artificial neural network provides a sophisticated mechanism for early identification of patients requiring clinical intervention, moving beyond the constraints of linear stochastic methodology. And it contains my data set contains several thousand patient records, each with 11 features. These include demographic like age, gender, clinical markers such as hypertension and heart disease, and lifestyle factors like smoking status and work type. As a dataset description, I targeted variable is defined as stroke and categorized as 0 and 1s, which 0 means no and 1 means yes. As we mentioned before, a primary source is Kaggle dataset containing structured clinical and demographic records. For the related works, traditional linear model fails to capture the complex combined nonlinear effects, so we use the statistical limitations and research gaps that are discussed fully on the paper itself. As input features, I have some several categories, which subcategories we can say as a demographic, age, gender, residence types, and even the marital status. The clinical and medical cases like hypertension, heart disease, BMI, glucose level, and lifestyle, which can be the work type and the smoking status. As the methodology, as a first step it was the missing value imputation, then the featuring engineering, then the categorical encoding, and the data setting. Here, as a training strategy, I use an 80-20 stress split for training and testing. Stratification is vital here because the dataset is imbalanced. It ensures that the rare stroke cases are proportionally represented in both the training and the testing sets. This model was trained over 50 epochs with a batch size of 32. The artificial neural network layers are the first one as an input layer, then as a hidden layer 1, hidden layer 2, and the output layer. The heart of this project is the ANN. So the first layer contains 64 neurons and the second layer contains 32, which I used a ReLU activation function to improve training efficiency and mitigate the vanishing grading problem. To ensure the model doesn't simplify memorize the training data, I drop out layers 30% for the first layer and 20% for the second layer. This part is also discussed, and now if we go to the experimental results, ROCs and AUC, looking at the vital results, the ROC curve shows the model's ability to distinguish between classes, which my model achieved a strong AUC score, which indicates its reliability in ranking high-risk patient correctly. We also look at the precious recall curve, and which curve the model performance under the pressure of the class imbalance. So, strategic insights, they are analyzing the critical trade-off of the priorities inherent in medical stroke risk prediction. And as a conclusion, this study demonstrates that ANN are power tools to stroke risk prediction by processing high-dimensional data. These models can complement traditional risk assessments and provide a second opinion for healthcare providers. Thank you for your time, Professor, and I hope I'm open to any questions if there are.